Okay, now there are two main things that we're going to do with that we can do with z-scores that we're going to focus on today. The first really neat thing about z-scores is that we can use them to tell us how a raw score compares quantitatively to other scores from the same sample or population. So I've talked about this already. Again, in the sample data, what we have are the attractiveness ratings of 100 men. So again, we get a group of women. We say, okay, women, rate how attractive these 100 guys are, and the distribution shows their ratings. For this example, we're going to focus on 3 guys, Chuck, Sean, and Brandon. We can see that Brandon is towards the higher end of the distribution, meaning that he's a pretty attractive guy. Sean is in the middle of the distribution, slightly above the middle of the distribution, so he's above average attractive, but certainly not as attractive as Brandon. And then poor Chuck is down the bottom of the distribution, pretty ugly looking guy, for being honest. Now, again, we were able to verbally describe Chuck and Sean and Brandon's attractiveness, but it took quite a bit of work and effort to do so. What z-scores are going to allow us to do is to compare quantitatively, or to describe quantitatively, how a score compares to other scores from the same sample or population. So instead of saying that, well, Brandon, we can see that he's at the far upper right end of the distribution, so that makes him a pretty attractive guy, maybe not the most attractive guy in this sample, but definitely towards the higher end. We could use one single number to explain that quantitatively. To be able to do this, what we're going to need to do is to transform the raw scores into a z-score. And that's what we're going to talk about next. How can we transform raw scores into z-scores to quantitatively describe how the raw score compares to other scores in the same distribution? So to do that, we're going to use the formula for z-scores. Now, yes, I think this is the first real formula you guys are going to have to memorize for the exam. Let's break down the symbols in the formula. Z in the formula is going to stand for the z-score. X, this X here, that's a symbol for the raw score. The X with the bar over it is a symbol for the sample mean. And the SX here, that's the symbol for the standard deviation. So what it is saying then, to calculate the z-score, you find the raw score, you subtract the sample mean from that raw score, and then you divide by the standard deviation. Remember orders of operation from your high school math classes. It's super important that you go in that order. Again, in the other order, it's not going to be correct. So to find a z-score, you must do it in the following order. The raw score minus the sample mean. And then once you have that number, then you divide by the sample standard deviation. Let's go through a couple of examples. And again, we're going to use the example we've been looking at throughout this PowerPoint so far. To actually calculate the z-scores for these raw scores for Chuck, Sean, and Brandon, we're going to need to know the mean and the standard deviation of the distribution. And this is the type of information that you'd be given on the exam. So again, you'd be told, in this distribution of scores, the sample mean is 60, and the sample standard deviation is 10. Chuck, Sean, and Brandon have these corresponding raw scores. Find the z-scores for those raw scores. To clarify, because these 3 raw scores for Chuck, Sean, and Brandon come from the same distribution, the mean and the standard deviation of the distribution will be the same. So this formula here is basically us taking this formula and plugging in the mean and the standard deviation that we were just given. So again, in this distribution down here, we are told that the mean is 60 and that the standard deviation is 10. So we're just plugging in the numbers into this formula here. So it's going to be the raw score minus the mean of 60 divided by the standard deviation of 10. Let's plug in Brandon, Sean's and Chuck's raw score into this formula here to then get their z-score. Okay, let's begin with Brandon. So Brandon has a raw score of 90. The question is going to be, what's his z-score? Well, let's plug in his raw score of 90 into this formula here that we were just looking at. If we did that, it would look like this. 90, his raw score, minus 60, the sample mean, divided by 10, the standard deviation. Again, you have to do it in exactly that order. Any other order, you're going to get it wrong. So 90 minus 60 gives us 30. And then 30 divided by 10 is going to give us 3. So Braden's z-score is 3. Let's do the same for Sean now. So Sean has a raw score of 65. We'll plug in Sean's score into the formula we've been looking at. So it's going to be 65, which is, again, his raw score, minus 60, which is, again, the mean of the distribution, divided by 10, which is the standard deviation of the distribution. We have to do it in that order. So 65 minus 60 gives us 5. We'll then do 5 divided by 10, and we get 0.5. Finally, let's find the z-score for Chuck. So Chuck's raw score is 35. If we plug that in, we get this formula here. 35, the raw score, minus 60, the mean, divided by 10, the standard deviation. We have to do the calculations in the numerator first. So when we do those calculations, we get 35 minus 60, which is negative 25. Then we do negative 25 divided by 10. And when we do that, we get negative 2.5. So Chuck's z-score, negative 2.5. Now, another thing that you might be asked to do is to transform a z-score into a raw score. So the idea is that you might be told this person in the data set has a z-score of 2.58. What is the person's raw score? Well, if we rearrange the formula that we were just looking at, we could find that fairly easily. So let's look at this equation. X is a symbol for raw score, remember? Z would be the z-score. Sx, standard deviation. And then X with the bar over it is going to be the sample mean. Here is the distribution we've been using. So let's just stick with this distribution for the next couple of examples. So again, the scenario is going to be, we're told that, we're going to add 2 more guys. 2 more guys just got added. We know their z-scores. What would their raw scores be? Okay, so let's begin with Andrew. We're told that Andrew now has a z-score of 2.7. The question is, what is Andrew's raw score? So to find his raw score, we're going to take this information, standard deviation, sample mean, and his z-score, and plug it into our formula. When we do that, we're going to get something that looks like this. Andrew's raw score is going to be equal to his z-score, which is 2.7, times the sample standard deviation, which is 10, plus the sample mean, which is 60. Again, remember order of operations from high school math. The only correct way to do this math is to do 2.7 times 10, which is going to give us 27, and then to do 27 plus 60. When we do that, we should get 87 for his raw score. Okay, let's do one more. Let's do Bobby. Bobby has a z-score of negative 1.4. Again, we want to figure out Bobby's raw score. So the formula would be, for his raw score, would be his z-score, negative 1.4, which you saw over here, times 10, the sample standard deviation, plus 60, the sample mean. The only correct way to do the math is to do negative 1.4 times 10 first. When we do that, we get negative 14. Then we could do negative 14 plus 60, the sample mean, and that's going to give us 46 for Bobby's raw score. Now, I want to stop for a minute and sort of put some of these numbers into perspective. All right, we've been talking about like transforming raw scores into z-scores, comparing z-scores. How does this all sort of come together? Well, what I want to look at is to see how Andrew's and Bobby's z-scores and raw scores compare to these other scores in the distribution. That is, we just got through seeing how Andrew had a raw score of 87. So if you're sort of going to plot Andrew's raw score on this distribution, it would appear right there, right? There's the raw score of 87 on this distribution. Similarly, Bobby, we just said had a raw score of 46. If we were going to put Bobby in this distribution, Bobby would go right around here, right? There's the raw score of about 46. Now let's begin by taking a look at Andrew. Andrew, we just said, had a raw score of 87. And, well, 87 is just below the score of 90. So again, Andrew's raw score is just below Brandon's raw score of 90 on the distribution. Similarly, Andrew's z-score of 2.7 would be just below Brandon's z-score of 3 in this distribution. So sort of getting a sense of how z-scores compare to raw scores. If the raw score is slightly below another, 87 compared to 90, so is the z-score, 2.7 compared to 3. Similarly, we sort of get a sense of how a z-score compares to the other scores in the distribution. A z-score of 3 or even a z-score of 2.7 is a fairly large number for a z-score. And so from what we were talking about earlier, we would expect a positive z-score of 2.7 or 3 to be pretty far above the mean of the distribution. And if we look at the distribution, yeah, that makes sense. The mean of this distribution is 60, so a raw score of 87 or 90 is pretty far above the mean of the distribution. Similarly, the z-score for the mean of a distribution is going to be 0. So a z-score of 2.7 or 3 is going to be pretty far above the mean of that distribution. I got a little carried away with that one, so I'm just explain this one more time. 2.73 are fairly big numbers for z-scores. We would expect these z-scores to fall far above the mean of the distribution, and that's what we find. Again, 2.7 and 3 are pretty far towards the upper end of the distribution, pretty far on the right side, showing how they would compare to the other scores in the distribution. Let's use Bobby as our next example. Again, Bobby had the raw score of 46. Here's where 46 would fall in the distribution. It would fall basically halfway in between the mean of the distribution of 60 and Chuck's raw score of 35. Similarly, Bobby's z-score of negative 1.4 would fall basically halfway between the mean of the distribution for the z-scores of 60. So the z-score being 0 in this case, and then Chuck's z-score of negative 2.5. Let me explain that one more time because that was confusing. Again, if we look at the z-scores, the mean z-score in the distribution is 0. Chuck's z-score is negative 2.5. And Bobby's z-score of negative 1.4 would fall here. So the key point, just like Bobby's raw score, falls basically halfway in between Chuck's raw score of 35 and the mean of the distribution of 60 for the raw scores. His z-score of negative 1.4 falls halfway in between the mean of the z-score distribution of 0 and Chuck's z-score of negative 2.5. Also, if we're thinking about the placement of z-scores in the distribution, the z-score of negative 1.4, the absolute value is modest, right? 1.4 is sort of, modest number, so we'd expect it to be slightly far from the mean of the distribution. And the z-score of negative 1.4 is negative, so we would expect it to be below the mean of the distribution. Well, here's again where Bobby's z-score would fall. It's below the mean of the distribution, so that makes sense. And 1.4, somewhat far away from the mean, but not like as far away from the mean as a z-score of negative 2.5. Sort of getting a sense, I hope, of how the z-scores line up in the distribution. Okay, for the next topic, we need to talk a little bit about z-distributions themselves. For all of the nitty-gritty details, you're welcome to look in the textbook. Basically, it goes far beyond what we need to know to understand the next topic. Instead, if you could just trust that these 3 points are true, we're going to be set. The 3 points that you need to know is that if you take any set of raw scores and transform each of those scores into z-scores, again, 3 things are true. First, the mean of this distribution of z-scores is always 0. The standard deviation of this distribution of z-scores is always 1. And the shape of the distribution is the same shape as the distribution of raw scores. Let's explain what these 3 things mean by looking at an example. Again, we're going to look at in this example is what happens if we take any set of raw scores and transform each of those scores into z-scores. So what we have here is a set of raw scores. To explain what I was explaining on the other side, on the previous slide, what we need to do is to transform those raw scores into z-scores. We basically need to calculate the z-score for each of these raw scores. Well, what information do you need to calculate a z-score? Well, from the formula, you need the raw score, you need the sample mean, and you need the sample standard deviation. So we could fairly easily calculate the mean of this distribution. We would do 6 plus 7 plus 4 plus 8 plus 5. We would divide that by 6, and we would get that the mean of the distribution is 6. We could also fairly easily calculate the standard deviation of this distribution of scores here. You would just plug in each of these numbers into the calculator like I showed you last week, do the right thing, and you will get the sample standard deviation of 1.4. So now that we know the mean and the standard deviation of this distribution, what we could do is to calculate the z-score for each of these raw scores. So let's do that now. We're gonna calculate the z-score of each of those raw scores. We're basically going to transform these raw scores into z-scores. Okay, let's plug this information into our formula. For the first raw score of 6, the formula, remember, is the raw score minus the mean divided by the standard deviation. So 6 minus 6 is going to give us 0. 0 divided by 1.4 is going to give us 0. Next, we have 7 minus 6. That's going to give us 1. 1 divided by 1.4 is going to give us 0.7. 4 minus 6, negative 2. Negative 2 divided by 1.4 is negative 1.4, and so forth and so on for the rest. Now, the point is, once we have the z-score for each of the raw scores, we could then find the mean and the standard deviation of these z-scores. If we were to calculate that, we would find that the mean of this distribution of z-scores is 0. And if we plug these numbers into our calculator, like I showed you last week, we would find that the standard deviation of these z-scores is 1. So that illustrates the first 2 points that I was talking about in the previous slide. The mean of any distribution of z-scores, if we transform all of the raw scores into z-scores, is going to be 0. And the standard deviation of that distribution is always going to be 1. For the last point, the shape of the distributions would be the same. So if we were to make like a frequency graph of these raw scores and then make a frequency graph of these z-scores here, the shape of that distribution would be the same. Again, that sort of explains the main things that we need to know from the previous slide. Now, the only reason we were really going into this information here for those key points is so we can discuss this sentence down here in green. These facts that we just described make it possible to compare raw scores from different data sets to see which raw score is farthest from the mean of its data set. In other words, which raw score is most impressive. We would find this out by transforming the raw scores into z-scores and comparing the z-scores. What the heck does that sentence mean? Here's the type of scenario that this information is useful for. Let's say I give you a set of raw scores from different distributions, and I ask you which raw score is most impressive. Which of these raw scores represents like the best score from any of the distributions? What you might be tempted to do is look at the individual raw scores and say, well, this raw score is the biggest number. It must be the most impressive raw scores from any of the distributions. But the key point is that you can't do that. To compare raw scores from different distributions, you must first transform all of the raw scores into z-scores and then compare the z-scores. Let's look at a specific example of this on the next slide. So again, what we're talking about now is the second thing we can use z-scores for. How do scores from different samples or populations compare to each other? Which score is most impressive? So here's the situation. Let's say I take students from 3 different statistics classes and look at their final grade in the statistics course. The student from my class received a final grade of 83. Student from an online class through FSU received a score of 85. And a student at the main campus had a final grade of 91. The question we're asking is, which of these three students did best in their statistics classes compared to their classmates? Now, we might be tempted to say, oh, well, it's student C. Their raw score was the biggest, so that must be the right answer. But that wouldn't be correct, or at least not necessarily. Let's stop and think about this. Those of you who have taken my classes before, what do you know about my classes? Well, you know that they are super hard, right? Most students get C's in my classes, and if you get a B, oh boy, you're something special. So the fact that this student got an 83 as their final grade in my statistics class, wow, this person's like a genius to have scored that high. What do you know about online classes at FSU? You know, fairly easy, not the hardest classes, but maybe not the easiest ones either. You know, to get an 85, yeah, you have to do the discussion board. Yeah, you have to do okay on the exams, but maybe it's not the hardest thing in the world to get an 85 on an online class through FSU. And what do you know about the classes at the main FSU campus? Oh my God, super easy. If you just show up to every class, you are guaranteed an A. So the fact that this student got a 91, I mean, that's not very impressive. All that means is that they came to like most of the classes. We don't even know if they even took the exams or not. Now, I'm exaggerating here, but what this is illustrating is that if we're trying to figure out which of these raw scores is most impressive, you can't look at the raw scores and compare those. Because again, the student who got the biggest raw score out of these 391, they might have done the worst compared to the classmates in their class. This 91 might be one of the lower scores in their class, whereas this 83 might have been one of the highest scores in my class. So how do we compare raw scores from different distributions? Well, what we need to do is to first transform those raw scores into z-scores. Let's go over this one last time. What we're talking about here is comparing z-scores from different distributions. To compare the relative standing of raw scores from different distributions, you can't just compare the raw scores. Instead, you must first transform those raw scores into z-scores, and then make comparisons between the z-scores. Again, if the question is, for example, which students score the highest relative to their classmates, whose statistics grade should we be the most impressed with, we can't just look at the raw scores and say, oh, well, 91 is the biggest raw score compared to these others. It must be student C score who is most impressive, because maybe they took a really easy class and their 91 was not very impressive really compared to their classmates. Whereas student A might have taken a really difficult class, and this 83 might have been one of the best grades in the class. Again, we can't compare the raw scores. What we need to do is to transform each of these raw scores into z-scores, and then compare the z-scores to see which of the z-scores was the largest. So let's go through a more simplified example. Here we have the raw score from a student on their first statistics exam and their first English exam. Question is, on which of these exams did the student do better relative to their classmates? Again, we can't just look at the raw scores and say that, oh, well, 45 is bigger than 38, it must be on the English one. Because it could be for the English exam, this was kind of a wimpy score, but for the stats exam, this was a pretty good score. Instead, what we need to do is to transform these raw scores into z-scores. To do that, we are going to need to know the means and the standard deviations of the exam grades. So here we have the mean and the standard deviation of the exam scores for the statistics class. And here we have the mean and the standard deviation of the exam scores for the English class. What we're going to do now is just to transform each of these raw scores into z-scores. First, for the statistics exam, the z-score for this raw score is going to be the raw score minus the sample mean divided by the sample standard deviation. Don't forget correct order of operations. It's 38 minus 30, which gives us 8. And then 8 divided by 5 gives us 1.6. Now let's do the same for the English score. For the English, the z-score for the English exam is going to be 45 minus 40 divided by 10. Remember order of operations, 45 minus 40 gives us 5. 5 divided by 10 is going to give us 0.5. So now we have the z-scores for the English test and then for the statistics test. We can then compare these z-scores to see which of their grades is most impressive. Well, the question that we want to ask ourselves is, which of these z-scores is farthest above the mean? In other words, which of these is the biggest positive value? Well, 1.6 is a bigger number than 0.5. So yeah, sorry, a z-score of 1.6 is farther above the mean than a z-score of 0.5. And so what that tells us is the following. The score on the statistics test is relatively higher than the score on the English test. She did better on the stats test and the English test relative to her classmates in those courses. So if you had a question like this on the exam, you would say something like that, yeah, relative to her classmates in the two courses, she did better on the English test than she did better on the statistics test than she did on the English test. All right, let's go through one more example because I know that could be a little tricky. In this example, we are looking to hire a new professor in the psychology department, and we ask in their applications for the professors to state their student evaluation scores from their previous universities. We can see in the applications that on their resumes that Dr. Smith had a average student evaluation score of 4.3 at his university, and Dr. Clive had an average evaluation score of 4.5 at his university. So the question is, which of these two professors should we hire, maybe based on their evaluation scores? Well, remember, we can't directly compare raw scores from different distributions because different universities measure student evaluation scores in different ways, and students at different universities might be harder or easier compared to others. So again, we are not allowed to directly compare the raw scores. What we have to do is to transform the raw scores into z-scores and then compare those z-scores. Again, to calculate the z-scores, we need to know the mean and the standard deviation of their distributions. So here we have that data. The mean student evaluation ratings at Dr. Smith's University are 3.8 with a standard deviation of 0.4. For Dr. Clive, the mean student evaluation scores at his university are 4.6 with a standard deviation of 0.2. So again, which of these professors had the better student evaluation ratings relative to the other professors at their universities? To find out, we need to transform their raw scores into z-scores. And we're just going to use the equation that we looked at the start of class to do so. So for Dr. Smith, to find his z-score, we take his raw score of 4.3, subtract that from the mean of the distribution, 3.8, and then divide by the standard deviation of 0.4. Again, we need to do correct order of operations, the information in the parentheses first. 4.3 minus 3.8 is 0.5. 0.5 divided by 0.4 then is going to give us 1.25. Okay. And for Dr. Clive, this is what the equation would look like. His z-score is going to be equal to his raw score minus the mean of his distribution divided by the standard deviation of his distribution. Order of operations, do what's in the parentheses first. 4.5 minus 4.6 is negative 0.1. Negative 0.1 divided by 0.2 is going to give us negative 0.5. So now the question we have is, which of these z-scores, 1.25 or a negative 0.5, is farther above the mean of the distributions? Well, we know that this first z-score, 1.25, is positive, while this one down here is negative. So this z-score is above the mean of this distribution, whereas this z-score is below the mean of the distribution. Not a great start. Additionally, this z-score of 1.25 has a bigger absolute value than this z-score of 0.5 for its absolute value. So what this is telling us, 1.25 is far above the mean of its distribution, whereas this z-score here is slightly below the mean of its distribution. So the z-score of 1.25 is going to be farther above the mean of its distribution than the z-score of negative 0.5, and so this z-score of 1.25 is going to be more impressive. So our conclusion would be something like this. Dr. Smith received higher evaluations compared to colleagues at his university than Dr. Clive. So it's Dr. Smith that we might choose to hire based on their student evaluation ratings. Okay, I think I'm going to leave it there for me. I know I said that I was going to talk about z-scores and percent and proportion, but I think we're just going to skip that section because it's going to be extremely difficult to explain over these PowerPoint slides. So the stuff about that on the study guide and on the practice problems, you don't need to worry about it. It's not going to show up on the exam. But here are the homework questions for Chapter 5. Don't forget to study for the exam. And then don't forget about the review questions and answers on Canvas that I talked about in the announcement on Canvas. Again, email me with any questions you might have. Good luck studying for the exam. We'll have the review session at the start of next week's class if you're still sketchy about this. But, yep, let me know if you have any questions and stay safe. I'll see you all next week.